besides lens distortion, what else that we talk about? Oh, okay, let me translate it. So Kunio mentioned, okay, so the image coordinates, they may have some shift over there. They may have some shift, and this equation doesn't really consider that type of shift. And so where does that shift come from, or how can you use to represent that shift? And we talk about that there are additional parameters, right? And those additional parameters to represent shift is shift has another term called offset. What offset we have to talk about? Yes. Principal point offset, yes. Okay, so we can include the principal point offset to the coordinality condition equation. So yes, we have two more, right? 6 EOP plus x0 and y0, two principal point offset, and we have 8 parameters. Right now we have 8 parameters. But what else? What else? What else do we have? Besides these 8 parameters, we have one more. We have one more. I accidentally tried to say one. So one more. We have one more parameter, which is what? It's over there actually. We have one more parameter, which is what? Yes, focal length. Yes, we have focal length as one parameter as well. Alright, so the coordinality condition equation, of course, if right now we assume there's no lens distortion, okay, and then in this case we have 9 parameters. We have 9 parameters. The xc, yc, zc, omega phi kappa as the EOB, and we have the x0 and y0 to represent the principal point offset, and we have also the IOP focal length. So we have those 9 parameters. So the 2D projective transformation is an equation simplified from the 9 parameter, those 9 parameters to the 8 parameters over here. So and actually here, how to simplify that? For the 2D projective transformation, actually it's less you can say less strict, and it is less strict. So it doesn't care about where your perspective center is. It doesn't really care about that. But however, you still need a certain perspective center because, like I said, it's the two plane that has a perspective projection relationship. So you still need a certain perspective center somewhere, but it doesn't really care where that is. And so, and also you don't really care about what's the shift, what's the principal point offset. But you still need to give it a certain principal point offset to decide the origin of the plane. You still need to decide it somewhere. So, which means that the principal point offset can be decided anywhere. You can decide it. You can decide it by yourself. It doesn't matter where you what's the coordinate that you have. So, what exactly does it mean by the simplification? So, actually, the answer is over here. So for the flat terrain and z, which means that the z is constant. The z is constant, right? The z is constant, and then for that is a flat terrain. And compare with that flat terrain to your image plane. And right now, like I said, you can change the image the principal point offset, which means that the image coordinates can be everywhere. You can change everywhere like that, and then there's only one parameter is reduced. Is the scale. I'll really mention scale. So, like I said, could be right. Your answer could be right, but your real answer is not right. So, the difference is at right now, because the z is constant, and so what can help you? What can help us to decide the scale? Which parameter can help us to decide the scale? Let's just assume. If these two planes are like this, a vertical photo. It is just a vertical photo. This plane 1, plane 2. What are the parameters that can help us, or that will help us to decide the scale? What are the parameters? Parameters, yes. What are the parameters that can help us to decide the scale? Should be very easy. You haven't skipped on. Focal length. Focal length. And then what? Inside. Which is the other one? I can help you to decide the scale. In order to decide the scale, we need focal length and what? No, no. So, Right.
Line height.
Yes. This one, right? Which is that. Okay? So, as you can see right now, because it's a flat terrain, so the scale can be decided by focal length and Z. And right now, 2D projective transformation, it doesn't care that it is a real camera. So this plane can be everywhere, and you can change this, which is focal length. You can change the focal length, but you can also change this. You fix this, and you can change this. So which means that these two, focal length and the flight height or Z, actually they are highly correlated. They are highly correlated to design the scale. So the simplification over here is just to remove one of them. It's just to remove one of them, and that's it. So it doesn't really matter which one you remove. And in this case, usually we'll say we remove the Z. Okay, we remove the Z, so that it becomes two-dimensional to two-dimensional coordinate transformation functions. Okay, so whatever remains, we tend to like simplify it so that this term becomes 1. And so you have 8 coefficients, okay, just like that. Okay. So the simplification is at the scale. So from the 9 parameters to the 8 parameters. Okay. Okay. Hopefully you can you can understand that. So it's actually very interesting. The whole discussion of that and also the how to prove the 2D projective transformation equation from the coordinate conjugation equation is in the textbook, in the reference book that I introduced to you guys, the one written by Wolf. It actually has a very detailed explanation about how to derive the 2D projective transformation function. So if you are interested in that, you can take a look. Okay, so any question till now? Any question? No? Alright, if not, then let's move on to, you can say something you guys may be more familiar with, which is the resolutions. Alright, let's talk about the resolutions. Yeah, let's talk about that. Alright, so to start, how many resolutions? What are the resolutions that we have in programming and remote sensing? 4 or 3? 3. 3, 4, 3, 4. Okay, 4. Okay, 4. Actually, we have 4. So, what are the 4 resolutions? Spatial and temporal.
Radiometric.
What? Radiometric? And?
Spectral.
Okay. Alright, so these are the 4, and I believe you guys are actually very familiar with that. And spatial resolution is sometimes we will just use, well, I believe you guys know it. Yeah, what's the spatial resolution? Isa. The pixel size. The pixel size is the spatial resolution. Like how many micrometer is 1 pixel size, right? So it's like that?
No. It's like the setup she has like the area.
Uh-huh.
The area that the setup will be.
Okay, so when you take a picture and then for the, you can say, for the digital image age, then in this case, all the pixels they are formed, all the image elements they are formed as pixels. And then for 1 pixel, if you project it to the ground, and then that pixel, what's the, and then that the area size that this pixel covers, that's called spatial resolution. Usually, that's usually called the spatial resolution. So sometimes we will call it, for example, like GSD, ground sample distance, like ground sample distance. And okay, that's the spatial resolution. Then I believe you guys know it. And then the highest spatial resolution that we can get from the commercial satellites is what? 0.5. Any more? Any guess? Any other guess? NG? No idea. You're not from remote sensing field, right? Okay. Which field are you from?
IESC.
No, I mean which kind of field?
Oh, natural resource management.
Okay, natural resource. Okay. So, and are you using any remote sensing data or? Oh, okay.
Starting.
Okay, that's good. Okay, so the discussion here should be able to help you. What's the highest resolution, spatial resolution that you can get from the commercial?
0.3.
0.3. Which satellite? Worldview 1. Worldview 1. Worldview 5? It's not much yet. Worldview 3 and Worldview 4. Right. Worldview 3 and Worldview 4. But Worldview 4 is dead already, right? Because of the some malfunction of the instrument. So Worldview 4 after not long after it launched and it couldn't work anymore. So what we have is only the Worldview 3. Okay, Worldview 3. Alright, so and okay, so basically that's the case. And then temporal resolution. What's temporal resolution? What's temporal resolution?
Revisit time.
The revisit time. Right? What do you mean by revisit time?
It means
Revisit time is yes. So revisit time is that how frequently that you can come back to the same location or take the photo at the same location. So which means that if you have the area of interest, how frequently that you can observe that area. Okay, that's the revisit time. So what's the highest temporal resolution from 1 single satellite that you can get currently?
10 minutes.
You guys. Right, yes, 10 minutes. So which is from AHI. So Himalaya, which satellite? Only 8? 8B? Himalaya 9. Okay, so Himalaya 9 and 8. Both of them, they are from Japan, and both of their temporal resolution is 10 minutes, right? 10 minutes. So, and that's the, you can say from one single satellite, that's the highest temporal resolution that you can get, okay? And radiometric resolution. What is radiometric resolution? Lisa? Beat? Beat? For what? Beat for what? Sure. You want to have like any more makeup bites? I'm serious, actually. If you want, you can get that.
It's about intensity, and you can divide the intensity
To what? To what? How many bits? How many bytes? What it decide? What is the thing that it decide? It decide the possibility. It decide the possibility of the values that you can use to describe the energy that you observed for one single pixel. Right? So, for example,